Welcome to today's special lecture. Can we please welcome the Honorary Secretary to take over proceedings from here? Thank you.
Thank you. Good evening, everyone. The President of the Ghana Academy of Arts and Sciences, past presidents of the Academy, vice presidents of the Academy, fellows of the Academy, ambassadors, high commissioners, consular and special desk officers for science and related matters, distinguished members of the diplomatic corps present, deans of faculties, researchers, lecturers, scientists, students, the media, Your Excellencies, distinguished guests, ladies and gentlemen. On behalf of fellows of the Ghana Academy of Arts and Sciences, Ghana's premier learned society, I warmly welcome you all to a GAS special lecture for 2022. We are streaming live via Zoom and on the Academy's Facebook and YouTube channels. From time to time, and as the need arises, the Academy provides the platform for the hosting of an occasional or special lecture outside its scheduled programs for a given year. This is a courtesy afforded the speakers after very careful deliberation by the Council of the Academy. Professor Dame Julia Higgins, DBE, gave a special lecture to a packed audience at the British Council Hall on the topic, The Responsibilities of a Scientist, on 8th February 2006. This was followed in 2007 by a special lecture on the topic, Discovery of a Unique Feature of Tonal Linguistics, the mid-pitch arrest phenomenon in the Krobo-Dangbe-Ga mother tongue of Southeast Ghana, delivered by Dr. Felix Konote Ahulu, Fellow of the Academy. On 3rd May 2016, Professor Kwesi Yanka, former Honorary Secretary and Fellow of the Academy, delivered an occasional lecture on the topic, the 3-year, 4-year school pendulum towards a stable public policy on senior high school education in Ghana. In more recent memory, we can recall Dr. Felix Konote Ahulu's History Surpasses Science lecture in honor of centenarian Dr. Emmanuel Evans Amfo, who was a fellow and past president of the Ghana Academy of Arts and Sciences, delivered on 31st January 2021. This year's special lecture is at the instance of Professor Herbert Graves Winful, a fellow of the Academy, who requested of Council the opportunity and approval for his friend of over 3 decades, who is visiting Ghana to deliver a special lecture as part of his activities while in the country. We are delighted that through the instrumentality of Professor Winfo, we have support from the University of Michigan for the organization of this all-important event. We thank you very much for the support. Now it is my honor to introduce to you the chair for this evening's session. He is Professor Kofi Sefadede, an emeritus professor in the Department of Food Process Engineering, University of Ghana. He is a fellow and currently the president of the Ghana Academy of Arts and Sciences. He is also a fellow of the International Academy of Food Science and Technology, as well as the Kellogg Foundation Leadership Program in Food Sciences. Emeritus Professor Sefadede was the Foundation Dean for the School of Engineering Sciences at University of Ghana. He was Dean of International Programs at the university and was Scientific Advisor to the International Foundation for Science. He served as Vice Chairperson at FAO WHO Codex Alimentarius Commission based in Rome and Geneva from 2011 to 2014. Before then, Emeritus Professor Sefadede led the Codex Committee for Africa from 2007 to 2011. He was also the chairman of a planning committee for the establishment of 2 universities, namely University of Energy and Natural Resources in Sunyani and University of Health and Allied Sciences, Ho. Professor Sefadede was the team lead consultant for the development and preparation of Ghana's second Millennium Challenge Compact. He was also the board chairman for the Millennium Development Authority for Ghana's Millennium Challenge Compact 1 and reappointed chairman for the Millennium Development Authority for Ghana's Millennium Challenge Compact 2 until January 2017. Currently, Emeritus Professor Sefadede serves as the chairman of the Food Subcommittee of the Board of the Food and Drugs Authority. Ladies and gentlemen, let's welcome the chairman for this evening.
Thank you very much, Honorary Secretary, for the introduction. Distinguished ladies and gentlemen, this evening is special in the program and schedule of the Academy, Ghana Academy of Arts and Sciences. We have a very special guest who will speak to us on a very intriguing topic. We are delighted and welcome our special guest into Ghana and also to the Academy. Past presidents of the Academy, vice presidents of the Academy, distinguished fellows of the Academy, students who are here, a privilege to be here at this time to listen to a Nobel laureate talk on a very special topic. Excellencies, distinguished ladies and gentlemen, we are about to listen to a lecture that I believe will help us think through matters that we encounter on a daily basis, but maybe have very little appreciation for it. The Honorary Secretary mentioned the role of Professor Winful for arranging this. And Prof, I would like, on behalf of the Academy, to thank you for this. He is a newly elected fellow of the Ghana Academy. We are proud of your initiative to invite your friend, and he agreed to be here with us. Thank you. So this evening, I am to introduce Professor Winful, who is he is going to coordinate our program this evening. And I'll introduce him and then invite him to introduce our speaker and take proceedings from there. Professor Herbert Graves Winful, a product of St. Augustine's College, Cape Coast, a fellow of the Ghana Academy, and a BS in electrical engineering from the Massachusetts Institute of Technology in 1975, and a PhD from the University of Southern California in 1981. From 1980 to 1986, he was a principal member of technical staff of GTE Laboratories in Waltham, Massachusetts. He joined the EECS department at the University of Michigan as associate professor in 1987, became a full professor in 1992, and was named a Thurnall professor in 1993. In 2019, he was named the Joseph E. and Ann P. Rowe Professor of Electrical Engineering. He has made fundamental contributions to nonlinear fiber optics, nonlinear optics in periodic structures, the nonlinear dynamics of laser arrays, the propagation of single-cycle pulses, and the physics of tunneling. He is a fellow of the Optical Society of America, the American Physical Society, and the Institute of Electrical and Electronic Engineers. His many awards include the 2020 IEEE Photonics Society Quantum Electronics Award, the Atta F. Thurman Professorship, and the Tau Beta Pi Distinguished Professor Award. His main fields of interest are nonlinear optics, photonic crystals, ultra-fast optics, tunneling, time and laser arrays. And so I invite Professor Winful to join me at the stage and introduce the speaker for this evening. Professor Winful.
Thank you. Thank you very much, Professor Sefadede. Thank you for... Can I get the first slides? Okay, so I would like to first thank Professor Sefadede, President of the Academy, and the Council of the Academy for agreeing to host this special lecture at such short notice. When we proposed this special lecture, the time for the regular lectures had expired, and so the council had to make a special decision to approve. So I thank you for approving it and for hosting this lecture. I'd also like to thank Mr. Francis Ankra, the Deputy Executive Secretary, with whom I worked on the logistics for this presentation. We exchanged maybe 100 or more emails over time, and I'd like to thank him for working so hard to make this a success. I'd also like to thank the Vice President of the Academy, Emeritus Professor Isabella Kwachi, also for her assistance and for helping to make this a reality. Next, I'd like to thank the French Embassy, particularly Dr. Florent Engelmann, who is the scientific attaché for the embassy, for his very hard work partnering with me to plan the itinerary and gaining the full support of the French Embassy in this endeavor. I thank the embassy for supporting Professor Mourou's travel. I'd also like to thank Alexandre Foulon, who is a person I first contacted at the French Embassy and suggested this visit by Professor Mourou. He enthusiastically accepted and worked very hard with me for over 2 years before he departed the embassy. And then Ms. Nina Amar has also been working very hard on this whole visit. So I thank you, Nina. Other people to thank. I'd like to thank the University of Michigan for providing funding for this effort, especially the African Studies Center. The African Studies Center has been engaged with Africa for many years, and one of its key enterprises is named the University of Michigan African Presidential Scholars Program. This program brings to the University of Michigan campus African lecturers who are early in their careers. They come to spend up to 6 months on the Michigan campus doing research, writing their dissertations, publishing papers, free of charge and free from the burdensome teaching loads. Over the years, over 50 lecturers from Ghana have participated in this enterprise. Other parts of our engagement with Ghana have been the partnership with the medical schools to create a postgraduate fellowship in OBGYN. This provided in-country training for more than 250 doctors in Ghana. And the great thing about this program is that more than 98% of those trained stayed in Ghana and are still practicing here. This was the effort led by Professor Tim Johnson at Michigan, who's shown in the middle there. And right now there's a library complex at one of the health universities here in Ghana that bears the name of Tim Johnson. So we thank him for that. It is now widely known that Ghana's former finance minister, the late Dr. Kwesi Botwe, earned his PhD in law from the University of Michigan. So he's one of the distinguished Ghanaians who have been trained at the University of Michigan. So that's part of my university's contribution to the development of our country. So I thank the university. If there are any UMAPS fellows around, could you please raise your hand so I can see. Okay, maybe there are none here. All right. Okay. So, I now come to the genesis of Professor Mourou's visit to Ghana. Professor Mourou and I were colleagues at the University of Michigan for over 15 years, and I've known him for over 30. He was the director of the Center for Ultrafast Optical Science, and I served as an associate director for education and outreach. For some reason, he would often say that I reminded him of Kofi Annan, Ghana's Nobel Peace Laureate and Secretary General of the United Nations. Of course, I was flattered, though I didn't think I deserved to be mentioned in the same breath as one of Ghana's true heroes. Oops, that's not, I could go back. Okay. Just a second while I navigate through this. Okay, sorry. Doesn't respond too well. Okay. Battery. All right, so at a party in Stockholm, the night before he was presented with the Nobel, I presented him with a kente stole, which he wore all night. He expressed to me then, and on several subsequent occasions, a desire to visit Ghana. I kept looking for an opportunity to make it happen. Finally, 2 years ago, I was approached by the organizers of the African Materials Research Society Conference in Senegal to help invite Professor Mourou to this conference. I saw an opportunity for him to stop in Ghana on his way to Senegal. I reached out to the French embassy on their website and got a very enthusiastic response a month later. The rest is history. So, all right. I will now turn to the subject of Professor Mourou's special lecture, Extreme Light, its benefits to science and society. Okay, so extreme light, what kind of light are we talking about? We're talking about laser light. Laser itself is an acronym. It stands for light amplification by stimulated emission of radiation. Now, the first word, light, is familiar to all, but light really is an electromagnetic wave. It's electromagnetic radiation. It can act both as a wave and as a particle. Now, amplification. So, amplification, you understand, is making something larger, greater. You have stereo amplifiers that amplify signal that's fed to them. Well, the laser amplifies by stimulated emission. And what is stimulated emission? Well, to understand stimulated emission, okay, well, lasers have tons of applications, including eye surgery. And today, we're at lunch at Buka Restaurant in Osu, and across the street, I saw this building, Interstar Eye Clinic and Laser Center. So they do laser eye surgery at that center. So eye surgery is one of the applications of lasers, and Professor Mourou's talk will expand upon his contributions to femtosecond LASIK. Okay, so stimulated emission. Okay. So an atom The model is that of a nucleus made up of protons and neutrons surrounded by electrons. Now, you can excite an electron from a lower level or low orbit to a higher level. The excited electron can then be stimulated to come down, can be stimulated by an incident photon, stimulated to drop down to a lower level. When it drops down, it emits another photon. The emitted photon is identical to the incident photon. So they're like twins, identical in every way. So from one photon, you now have two. These two photons then travel along, they encounter other atoms, and stimulate more emission of identical photons. And so you amplify all these photons. They are identical in every way. They add coherently to get the purest form of light you can imagine. And so that's stimulated emission, and that is the basis for the operation of the laser. Okay, so now you all understand how lasers work. So you can understand better Professor Mourou's talk. I'll skip these cartoons and go to some other things you'll hear about. Power. You're all familiar with 100-watt light bulbs. The power that Professor Mourou will be talking about is huge, many orders of magnitude greater than the power of a light bulb. He'll also talk about the concept of compression pulse. So suppose you have a given amount of energy. Energy is measured in joules. This energy over 1 second of time is power. If you take the same energy and you squash it into a shorter time frame, you increase the peak power. So these two pictures show two pulses with the same energy. One is shorter than the other, and the shorter one has greater power. Okay. There'll be very short durations. We'll go from 1 second to 10 to the minus 21 seconds. Okay? 10 to the minus 21 of a second is a zeptosecond. And in between, you have milliseconds, microseconds, femtoseconds, etc. And then powers. You will hear about extraordinarily large powers, kilowatt to zettawatt. A zettawatt is 10 to the 21 watts. Unimaginable. Okay. So now you're all set to understand everything that follows. Okay, so let me now introduce my friend and colleague, 2018 Nobel Prize winner, Professor Gérard Mourou. Professor Mourou was born in Albertville, France in June 1944. He received his BS in physics from the University of Grenoble in 1967 and his doctorate from the Pierre and Marie Curie University in Paris in 1973. In 1977, Professor Mourou joined the Laboratory for Laser Energetics at the University of Rochester as a research scientist, eventually becoming a professor at the Institute of Optics. At Rochester, Mourou worked with an exceptional group of students to make fundamental advances in ultrafast optics and optoelectronics, culminating with the invention of chirp pulse amplification, or CPA, work that led to the award of the 2018 Nobel Prize in Physics that he shared with former student Donna Strickland. In 1988, Professor Mourou moved his entire group of 14 students, research scientists, and even his administrative assistant to the University of Michigan, where he became the founding director of the NSF-funded Center for Ultrafast Optical Science. It was at Michigan that the technology of CPA grew up and matured, finding new applications in science, industry, and medicine, applications that include the femtosecond intralaser technique that has now been used on millions of patients throughout the world. For this femtosecond LASIK development, Professor Mourou and his team received the Golden Goose Award in the United States just a few months ago. In 2004, Professor Mourou retired from the University of Michigan and returned to France, where he became director of the Laboratoire d'Optique Appliquée and a professor at the École Polytechnique. A true visionary with a passion for intense ultrafast lasers, he championed the creation of the Pan-European network of petawatt-class lasers called the Extreme Light Infrastructure to make available the most powerful laser systems based on CPA. In addition to being a great scientist, Professor Mourou is an extraordinary human being who displays great empathy and cares deeply about his students, his colleagues, and the people who work for him. He's a man of big ideas who has the energy and drive to turn those ideas into reality. Never one to rest, he always believes that the best is yet to come. Professor Mourou's numerous accolades include the distinction of being made an officer of the French Legion of Honor in 2020. He's a member of the National Academy of Engineering and has won every possible award in optics and laser physics, a small sample of which includes the Arthur Schorlow Prize in Laser Science, the Charles Towns Award, and the R.W. Wood Prize. But I'm sure you'll agree that winning the 2018 Nobel Prize in Physics is a cherry on top of a truly spectacular career. Never one to rest, he always believes the best is yet to come. So please help me welcome the 2018 Nobel laureate, the A.D. Moore Distinguished Professor, Gérard Mourou.
Yeah. Well, good evening. It's truly an honor and a real pleasure to be here. And it's a real pleasure and honor, but to be here was a big effort. You know, something which was started about 4 years ago after I received the Nobel Prize. And Herb was, of course, extremely instrumental behind this. And that's the reason I also, beside Herb, I would like really to thank the Academy here, all the members and the head of the Academy, the chairman of the Academy, and the honorary chairman of the Academy, and so on. And anyway, and the students that I see, and boys and girls, and that's very, very important for science and for physics. As you will see, you know, I shared the Nobel Prize with my students, you know, and so this was, of course, especially important for me. But anyway, I cannot really thank everybody, but I'm really glad to be here. And plus, you know, it's absolutely new part of the world that I came here with my wife, Marcel, for the first time. So I'm going to talk to you about what I did and what led me to get the Nobel Prize. First of all, what I, you know, like I always said, you know, to students and so on, there is no tricks to get the Nobel Prize. You have just to do one thing, you know, to be passionate about what you are doing, you know, and believe in science, believe in our case, in physics, but you have to be passionate, and that I'm really glad to talk to all the students that were here. By the way, this is one of the things about the Nobel Prize, which is very nice, is it's not obligatory, but it's something they highly, highly recommend. Is really, when you get the Nobel Prize, you have to go, and talk to the students and talk to everybody, and use of this prize, to attract students and to make the world better, if you're a scientist and so on. So I'm really glad to be here. So I'm going to talk about light, and I was very fortunate to have already a very good professor, of course, Herbert Winful, to give you the rudiment of light and lasers, and I'm going to use it because. So first of all, I'm going to talk about extreme light, light which are extremely powerful like 1,000 times the power produced by all power plants in the world. So that's powerful, right? I can say that. I can even say it's extreme. And I will tell you a little bit how we do that, okay? But what's important also is how are we going to use it? How is it going to be benefit our society? So it's one thing, of course, to invent something, but also it's another thing to come up with very nice inventions which benefit society. And in fact, the motto of Alfred Nobel was he wanted to devote his prize for the benefits of human being, okay, for the greatest benefit of human beings. So this is another thing about the Nobel Prize. So when I got this phone call, you always start from a phone call, I was on my way to the swimming pool. I like swimming, like Professor Winful said, I am. And so my secretary said, Gérard, come back because you have a phone call from a foreign country. Okay, so I went back and went to my desk and picked up the phone and find I had the chairman of the Nobel Committee saying that you are the winner of the Physics Nobel Prize 2018. Wow. This, of course, is like a ton of brick, coming on you. And he said, this is not it. You are going to share it with a student, one of your students, Donna Strickland. And that was really, of course, like a cherry on the cake, because for a man to get a Nobel Prize, the Nobel Prize is 120 years old. Okay, so on average you have three for the physics. You have three laureates here. So you see that it's a lot of men with the Nobel Prize. Okay. But Donna was the third woman to get the Nobel Prize, behind Marie Curie and Maya Gopper-Mayer. And Donna was the third one, over 120 years. So I could die at this moment, you know. I was a Nobel Prize. I was a teacher of the third woman getting a Nobel Prize. I say, okay, now you can die. Anyway, but it's true, you know. It's absolutely true. So, and also it was good because I have also very good friends among them. You have Professor Herbert Winful, and with Herbert, you have to go to Ghana and give a talk, okay? And although the agenda, you know, you get 100 invitations, you know, when you get the announcement, just like 100, okay, maybe more. I'm sure it's more than that. And they grow over the year. So coming to Ghana, you know, was kind of a treat to find, you know, because you have so many other universities, you know, which are inviting you, you know. So it was something special that we had to do with my secretary, Cathy Sarrazin. So anyway, so I'm here, okay? And I'm going to talk about what I'm passionate about, of course, physics, about light, about lasers, and the novel application of lasers, okay? Okay, so, by the way, here you see myself with Donna Strickland on the stage, you know, being happy about. And so now, yes. So I'm going to talk about laser. Professor Winful gave a very nice introduction, so I have really a little amount of work to do. And what I'm, the first, we have to start by the beginning, and the beginning started by this man, you know, Ted Henge. You know, in 1960, Ted Maiman, I'm sorry, Ted Henge is not a very great scientist. Ted Maiman, of course, I'm sorry. In 1960, Ted Maiman was at the Hughes Aircraft Laboratory and demonstrated for the first time laser light. Laser light is a special light. It's a very organized light, you know, and a lot of time I take the analogy with light, you know, which is normal light, which in fact is kind of a bunch of photons. Photons is the particle of light. And, but all these photons, you know, were raining on you. They don't know each other. They don't interact with each other. They're all different. They go in different directions and so on. So that's normal light, right? It's what we call incoherent light, okay? But light, the laser light, it's a very ordered light, you know. All the photons are almost identical, Okay? And they are together, they move, in a unified way together. And so it's very much like if the normal light is much like a marathon, with all these runners, running the marathons, all different and going in different speeds and blah, blah, blah. They don't know each other. Laser light is like marching soldier. They all go at the same pace. They have all the same uniform. So this is laser light. So now you can understand it's very different, and you can understand that now it's a revolution, that light, laser light, is going to revolutionize, the application of light, because it's completely different than normal light. So, as I said, the first person who demonstrated for the first time a gadget which was capable of producing on-demand ordered light. And and you see that Ted Maiman has this little gadget, which is very simple. It's composed of a flashlight, the type of flashlight that you're using to take pictures, and a gain medium. In this case, it was a ruby, and a flashlight, as I say, but flashlight, and two mirrors. And two mirrors are going to enhance, the stimulated emission that Professor Winfrey described. So it's a simple gadget. And, but with this gadget, you can do things widely different. One thing, very spectacular, which is very important for physics, but also for the rest, is you can take this, shine the light on atoms, and you can slow down atoms. In physics, we call. So normally, atoms, moves. You have in the air, in the atmosphere, they move typically a few hundred meters per second. Okay. When you cool them, they cool and they now, they are able to. We cool them with lasers. The speed, the velocity will go to millimeters per second, a fraction of a millimeter. So you cool the atoms, you slow them down, and you do that with lasers. And that led to a huge, large amount of application, but I'm not going to describe it. But the other things which is spectacular about light, about this type of light, about a laser, is you can do the conversions, accelerate atoms up to the other limit, which is the speed of light. So you see, this is amazing because damn it. Yeah, okay. I'm moving. No, this is going the opposite ways. Okay. So, as I said, you can slow down light, or you can accelerate light to the speed of light. And you cannot, and then you have to stop because you cannot go beyond that. Okay. And so you see, if you express the energy, we like really to express things by energy and things like that, units that we know. In the first case, you slow down, as I said, the atoms, and the energy, moving, is on the order of a, pico electron volt. Electron volt is a measure of energy for us. And when you accelerate these atoms, we can go to giga electron volts. So picosecond electron volt, giga electron volt, and in the future we'll do better. So we have about, with 1 electron volt, photons emitted by these lasers, we can cover a range of more than 20 order of magnitude. This is enormous. Okay. Talking about the first part, I'm going to talk about the second part, which is now when we are going to accelerate the particles to the speed of light. Okay? So they become what we call relativistic. Okay? Okay, so I'm going to try to do that. So, and we can do that. You will see that we can do that with light, but we had to change, we have to modify it. We had to really provide, we had to transform the light, And the light that we are going to use are extremely short bursts of light. Okay? Short burst of light, and the burst of light typically 10 minus, we started with 10 minus 9 nanoseconds. Then we went to picosecond, 10 minus 12 seconds. Now we are easily at 10 to the minus 15 seconds, which is the femtosecond. And we're marching toward the zeptosecond. But already the femtosecond that we are using now every day, and you will see the application, and is very short, very short. It's a millionth of a billionth of a second. During this time, the light propagates the dimensions of a red cell, and so this is very, very short, of course. And so you say, well, why do we do that? Okay. I will say that, for instance, big applications was first to look at reactions, because right now when I see something that is because I have photons coming to my eyes, and they trigger some chemical reactions in my eyes. And that's the reason I see you, okay? And I have a lot of exciting work, trying to understand, trying to take picture of these reactions, okay? And chemical reactions and so on. So this to help men to understand. But the other things that you can do is you can produce very high power because, as Professor Herbert Winful said, power is energy divided by time. So because we are able really to make it pulses extremely short, then you can get huge amount of power. Power, as I said, 1,000 times the power of the total power produced in a globe, you know, in all these power plants around the globe. And in order to do that, as I say, okay, we have to produce these very short pulses. And this, of course, is not simple. And what we do is we produce first a seed pulse, you know, small pulse, and the pulse will be also femtoseconds, and then we are going to amplify it. But as we amplified, that was the problem, is the amplifications. Because as we amplify a short pulse, of course, the pulse becomes too powerful. The intensity becomes too high, and you break down the laser. So it's not, we cannot do that, of course. So this is where we had the idea to say, before we amplify the short pulses, first we are going to stretch it. We are going to stretch it 1,000,000 times. When we started with, and this was, we started with Donna, it was 100 times. And then 1,000 times, 1,000,000 times. And so it means what? It means that now the seed pulse are 1,000,000 times less intensity. And then we could amplify now this weak pulse in the lasers without breaking down the amplifiers. And of course that changed really the amplification technique. And then once we have this very elongated pulse, we are going to compress the pulse, and this is where we get this very, very high intensity pulse. So that was really the trick, and it was a simple thing to do, and but simple on paper. But of course, you know, you have a way to show it, you know, after in reality. But anyway, so that works very well, and now this. By the way, the pulse is chirp pulse amplification. Chirp, you know, it's like birds, right? Bird chirped because as they really send their nice cries, they chirp it as they, you know, send their signal. So after we demonstrated the CPA, it was a big thing, because we knew that we could produce the largest peak power. With this very high peak power, we could produce the highest temperature. We could also produce the pressure that we are able to produce now is maybe, of course you know the Eiffel Tower, right? What we have in Paris, okay? We have, if you take 10 million Eiffel Tower on a finger, this is the type of pressure we can produce. Of course, over maybe a small size of over a microns also, but nevertheless, okay, we can do that. And so this, it's the other things also. As we are going to show you, we're able to accelerate particles, you know, to the speed of light, So, and we can do it very well and get extremely high accelerations. Very important also. So now, I don't know if you see everything. You see. Have here the intensity as a function of years. Okay? So 1960, of course, laser came, but the intensity was of the order of 10 to the 8 watt per square centimeters. You know, now it's very modest, but in those days it was very high, of course. So then some new techniques came up. You know, the refinement, but the machining that we could do was pristine. It was incredible. Very, very, very precise. It was, and so we had the idea to use it, you know, as, you know, to cut as a in the medical, you know, to make a bistouri, we call that in France, this very, very sharp knife, okay, and with light. Okay. Is being used now in all, I mean, one of the very nice application is for the eye surgery. And I was pleased to see that even here, you know, you do surgery with lasers, okay? And you are doing this surgery with with precise, and so you can work with, you know, of course, in your eyes, you don't want to have it has to be a very, very sharp knife. Okay, so this is a very, very important application. You had millions and millions of patients now being, you know, having surgery by using the femtosecond lasers. Now, if you increase, you know, I'm following the curve, if you increase the intensity, then something else happens. Okay. As Professor Winful said, the light is electromagnetic, is radiations. That means it's composed of electric field and magnetic field, and they work in concert. And so. The electrons, you know, but when you shine light, you know, onto something, of course, you know, everything is composed of electrons, protons, neutrons, as Professor showed us. And so the electric field, you know, agitates, you know, the electrons. And it is because these agitations, really, under this agitation, you have light, which is produced by this agitation. You have radiations. And that's the reason you can see the object and so on. So but here, you know, when we're using normal light, the agitation of this velocity of this electron moving around the nucleus, okay, it's not fast. But when we're using light, because the field is much, much higher, these electrons really start to and becomes relativistic. They move at the speed of light. And that is changing the physics of the interactions, light-matter physics, matter-light physics, entirely, because now the electrons, you know, can be moved at the speed of light, okay? And now if you If you go a little bit higher, okay, then you have the protons, and we have electrons, we have the proton in charge, and also is going to be, the light is going to act on the protons, and the proton will be able also to go at the speed of light, and you will see chart. Now, if you, this comes the interesting part, if you crank up the intensity even more, okay, then you are coming in this orange part. And here, so high, the intensity of light is so high that you materialize light. And you break down the vacuum. Okay, so this is something which is, you know, people were thinking about that, you know, more than 50 years ago, okay? And so you can demonstrate that, in fact, the light becomes matter, becomes electron and positrons. So this is to give you an idea of what, so now I'm going to go through these applications, but I will show you also more societal application, because this is what we need. So anyway, so with this now, the lasers at the beginning was dealing only with the electrons running around the nucleus, okay? And the nucleus, it has no effect on the nucleus, because the forces, you know, which are binding all the protons and neutrons together, you know, are too large, okay? But now, we start now to be in a regime where we can act on the nucleus itself, okay? So this, we are in what we call in the subatomic physics. And this is, of course, extremely exciting. You are going to see these enormous applications. Now, if I want to go to very, you know, I showed that we were, you know, we were into the green, the yellow, and orange. If you want to go to amplify your pulses to go into this yellow and orange part of the curve, then you have, of course, to amplify the pulse even more. So you have two ways to do that. You have one way is to add energy to your pulse, keeping the duration of the pulse constant, or the other way, to find a trick to make the pulse even shorter, okay? We start with femtosecond, and now we likely to have to go to the attosecond, 10 minus 18, zeptosecond. And the reason we do that is because we want to get a higher field, higher intensities. And that, so this is really now what our drive, okay? So, and so if you want really to increase, as I said, the intensity of the pulse, you have to compress it. Compress it, so a short pulse is composed of, you know, oscillations, and the number of oscillations typically for the pulse like we use is about 10, 20 oscillations, light oscillations. So we like to go to 1 oscillations. And so we have a shorter pulse. Now, I'm not going to go into the details. We can do that, okay? We can produce single cycle pulse. Now, and I won't have the time really to go back. But once you are on a single cycle, also pulse, what you like to do is try to compress it again. And how can we compress it? Well, we have what we call, we compress it by what we call a relativistic mirror. You know, we know what a mirror is, right? You're looking at you every day when you're shaving yourself or whatever. But we wanted to develop a mirror which is moving at the speed of light. And if you have light going into your mirror, laser light going into your mirrors, moving at the speed of light, of course, then what you are going to do, you are going to compress the incident light. And you should be able to compress it by a factor 100, maybe 1,000. So, so this is, I'm not going to go into the detail of this because it's not a little bit, but this is the idea. We can make a mirror, a moving mirror, because the laser pulse is so strong, the intensity is so strong that now this mirror moves at the speed of light. And that was a factor 1,000, which means that we could get zeptosecond pulses. Zeptosecond, you know, is 10 minus 21 second, which is extremely cold. So, and so what do you do with that? Okay? What do you do with a zeptosecond pulse? Well, you can do extremely important things. I'm going to show you that. Okay? First of all, you know, if you have 1 joule in 1 zeptosecond, then the peak power is zeta watt, 10 to the 21 watt, which is enormous, of course, which is zillion times the power of all the nuclear pulses, you know, nuclear plants in the world. Is in fact, billions of photons. Okay, so let me, I'm going now really to show some real applications. The applications, one of the nice applications is really, we told you that we have electrons, we have protons, and we have, electrons, you know, going around the nucleus, but in the nucleus you have protons and neutrons. And these elements can be very important if they are accelerated. And so in order to, for instance, a very important application in the medical world is if you accelerate protons into energy of the giga electron volt, 10 to the 9 electron volt. Okay. That is, you take the pulse, your high intensity pulse now to do that, and you focus that on a very simple thin films of matter, you know, because everything has electrons and protons. And then you can produce protons because with this phenomenal pressure, you can produce very high energy protons. And protons that reach this relativistic limit, proton becomes relativist, and it's what is nice is if you really want to accelerate protons, to do that now, you know, to the giga electron volt regime, you need an enormous accelerator, which is about 1 kilometer in length, you know. But with the laser, you can really compactify the accelerators enormously because you need a small fraction of a millimeter to do it. Because, once again, because the peak power is so large. Okay? And so on, you understand that it starts to be very exciting, because now in medicine, we are using, electrons, protons, and so on, okay? And we are using electrons and X-ray, for instance, for therapy. If you are cancer, what we like to do is to burn the tumor. But now, if you have tumors, say, in the brain, unfortunately, to burn the tumor, you can use electrons, you can use also X-rays to burn the tumor. But the problem is when you do that, you are going, the tumor is within your brain, you are going to, affect, badly the surrounding tissues. But if you are using protons, it's not going to be the case. You can focus the beam on the tumors, but you are not going to affect the surrounding tissues. This is a very important application. Also, there is also nuclear therapy is used for other applications and so on, and diagnostics. So this is very important. So now we can use, that's one, so I show you this very nice application in the medical. Now the other applications could be, is for trying to produce abundant, clean energy. You know, but now we have a problem, right? We have a very serious problem on our planet. We don't know how to produce clean and safe energy. We all believe, because, if we are using fossil energy, of course, we are producing this carbon dioxide, which is really ruining, the atmosphere, and it's at the origin of climate change and so on. And so this is bad. Okay, carbon fossil fuel is bad. Okay, so one which is very good, of course, is nuclear energy, because with nuclear energy you don't produce carbon dioxide. The problem is, of course, you are producing other things, but we can really solve the other problem. I will show you in a minute. Okay, so with this very extreme light, high intensity light, if you can produce neutrons, then what you can do fission, nuclear fissions. Okay, but we can do nuclear fission not on uranium like we do now, but on another actinide material like uranium, on thorium. Okay. If we are using uranium, of course, what we are going to do, we are going to have to produce some toxic waste. Okay. And these toxic wastes are going to stay with us maybe a million years. So it's not very good. Okay. So instead of using uranium, what you can do is using another element, which is thorium, okay, which produce much less toxic waste, and the toxic waste lives in a range of 500 years instead of millions. So this is, of course, 500 years if we want really to, you know, bury or the waste. We can really conceive, you know, can conceive places which can really last 1,000 years or 500 years. I mean, with the cathedral, with pyramids and all, we know that man can really build things which can last for 1,000 years. Okay, it's not a problem by using thorium. Okay, the other things is, of course, if you have. Oh, by the way, this is something interesting. I didn't say it, but if you have nuclear energy, I just want to say two things. Nuclear energy, of course, take a nuclear power. You know, you need something like fossil power plants, you know, based on coal and so on, fossil materials. Then, if you want to produce a gigawatt, you know, electricity, then you have to have 100 trains for 100 wagons to produce a gigawatt for a year. 100 train, 100 wagons. So, and that, of course, is going to produce tons of cubic meters of carbon dioxide, so which is no good. So for the nuclear energy, now, if you are using nuclear energy, and if you are using uranium, well, with uranium, you are going to use only 300 tons instead of million tons in the case of coal. Now, if you are using thorium, instead of the thorium is much more efficient, it will suffice only a ton of thorium. See? So that's the idea of, it would be a good idea to switch to thorium instead of uranium. Okay, so now, if we are doing now nuclear energy, then we are going to use nuclear fission. Nuclear fission works in a very simple way. You have your atoms of actinide, like uranium or thorium, and then we are using your neutrons that you can produce with the laser, with the high intensity laser, with the extreme light laser. And these neutrons are going to fission uraniums or thoriums, you know, and produce neutrons, but produce energy as well. But the other things that, and this is a problem, that is going to happen is that these neutrons could be captured by the nucleus. And then they are making an element which really lasts a long time. In the case of uranium, it can be millions of years, okay? But in the case of thorium, 500 years, it's not that bad. So this is what happened, and that is what is the problem right now by using nuclear energy. So, but what you can do is you can transmute also this big, this what we call the minor actinide. Minor actinide are the nucleus that are produced with under the actions of neutrons. And you can really transmute them with the neutrons, and you are making smaller elements. And and with a lifetime of now you know, hours, days, and so on. So this is not, this is not a problem. And finally, so I would like to show you, I showed the applications of extreme light, you know, in the medical application light, you know, to produce fissions. And now I'm going to show extreme light to solve the problems of the other big problem that we have on the planet, is to have to get rid of space debris. You know that since the beginning of the space age, you know, which was started in 1957 with the Sputnik, okay, we sent something like the equivalent of 4 Eiffel Tower in space. Okay, so so that has produced millions of orbital debris. These debris, they can be big, they can be small. If they are big, you know, we have ways, we have ways to get rid of them. But if they are simple, if they are very small, then it becomes, and numerous, then it becomes very difficult. And so the laser can be used, and extreme light laser can be used for that. Because these debris can be in a regime of centimeter or fraction of a centimeter. The problem, they can be small, but you know, they go like 10 times the speed, the velocity of the fastest bullet. So, of course, they can be very, very dangerous. The idea is really to use the lasers not to blow the debris, because you can, if you blow, you are going to make even more debris. So you don't want that. But what you want to do is to produce a small ablations. An ablation, you can ablate the debris over a small part of the debris. And these ablations is going to produce a rocket effect, and the debris will go into the atmosphere where it will be burned. So this is what the idea we propose, you know, to get rid of these debris. So now I'm going to stop here. Before I can stop, I said that, you know, what is nice when you get Nobel Prize, you have the possibility to meet very other people, and sometimes very, very important people, like the Pope. And the Pope, of course, you know, takes, you know, really is someone who would like really to solve the problem that we are facing, that the human world is facing. So we were invited with Donna, and we told to the Pope about all the application in space, you know, in production, in energy productions, and so on. And he liked it a lot. So I'm going to stop here. In conclusions, this extreme light, you know, the fact that we are able now to produce very high intensity light, find all kinds of applications, you know, in ophthalmology, but also in energy productions, and also cleaning the space and so on. So it has a lot of applications, okay, for the world. And it carries away the best hope and opportunities for the future of science and society. And I guess I'm going to stop here. You must, at this point. Thank you very much for your attention.
Thank you very much, Professor Mourou. Now, Professor Mourou will be happy to take a few questions. So, if you have any, please
And I would appreciate if the few questions were coming from the ladies. I want to have another Donna Strickland in the audience. But, I mean, a man can do it, okay, also. So don't be bashful.
now you don't want us to call on you to ask a question, right? So please, students, I'm sure you have questions. Oh, okay.
Yeah.
Thank you very much, Prof, for the fantastic talk. I mean, those of us who are laser enthusiasts, we really enjoyed it. Now, apart from the chair post amplification, there has also been other amplification methods that have been developed over the years. For instance, the multiphoton intrapulse interference scan, which also amplifies. I think it was developed by the Dantus group in Michigan State University. And this question is to both you and Prof. Winful, because I am not a nonlinear expert in the physics. But how different is this chair post amplification with, for instance, the MIPS and the time domain tychography that was also developed by the Stellenbosch University in South Africa? If I don't know if you're familiar with that. Thank you.
Well, I mean, right now, in terms of amplifications, I would like to be challenged, of course. Okay, but chair post amplification is really the best right now, what we know. But of course, if with chair post amplification, you have to work in a given spectral range, okay? So, of course, it works for light. It doesn't work for, you know, radiations at radio wave or something like this, okay? Although he could, but so that is in fact I think, or maybe in X-ray, for instance. I think the chair post amplification is certainly the best way to amplify light. Light being, I include X-rays as well, okay? Yeah, okay. Go ahead.
Felicitas. So with regards to the space debris, then the laser, could you please throw more light on that? And also with respect to any limitations that you've come across in your proposal to curb space debris?
Yeah. I didn't. Could
So,
you repeat the questions?
yes, so with the space debris that
Yes,
you showed,
space debris.
yes, please could you throw more light on that, and also the limitations that you've come across with your proposal in curbing that whole concept of space debris?
Yeah.
What limitations you have come up?
Yeah.
This proposal.
Oh, absolutely. I mean, the limitation, of course, is about the average power of the laser. You know, because we are, if you have millions of debris, right, you need the lasers, you know, which really can shoot at a higher rates. And it has to shoot at high rate, but also you have really to produce a significant amount of energy per pulse. So that leads to a laser with high average power. We have a peak power, that's no problem, but we need also the average power to clean if we have a lot of debris to deorbit. And that is a problem, actually, you know. But you have seen that, I went very fast, of course, but the laser, the structure of the laser that we want to use, in fact, is composed of fibers, which are what we call phased. Fiber phased, okay? The reason we are using fiber, because fiber amplifier, because fiber are very relatively easy to cool. So we can increase the rate this way. And but the problems is, of course, average power. But when we talk about average power, you have also to talk about efficiency, wall plug efficiency. And if you are really, if you have to embark, if you have to have a laser system, like I showed, composed of fiber and so on, you need average power of, in 50%. 50%, right now the lasers in general, are really, laser is a formidable tool, but it's inefficient in general. Okay, it's a fraction of a percent very often. With fiber, we can do much better than that, but still, you want to have something which is as a low, as a good efficiency. Okay, efficiency in a range of 30, 40, 50%. This is a must if you want really to use a laser, to use something in, if you want really to embark it on a spaceship, it has to be efficient. So, but this is where the problem is. But we will solve it. I'm sure we will be able to solve it. It's very important that we clean the space. Because right now, all this, even if you have a little bit of paint, going at 10 times the speed of the fastest bullet, I mean, if it hurts something, it's going to damage it. So it's a very, very, very important for the space program now to work on trying to clean the space, because it's bad for the satellites, which are already there, but can be also very bad, dangerous for the astronaut as well.
Professor, thank you so very much for your presentation. The talk was excellent. I want to ask about what it takes to get to where you are. from the idea, when you get an idea, when you have a concept, I can imagine what it takes to come up with even instrumentation to test that concept before you finally show that something can be done. What are you doing in that period? What is your research group like? How do you keep people motivated so that you can come up with these great things?
Yeah. For instance, between the concept and the Nobel Prize, we had 35 years. And this is very common, very common. Okay, but you don't want in your life to have the objective. The objective is not a Nobel Prize, you know, because the objective is really to do something meaningful for the society. Okay, and you know, the time it takes really to get from the idea to really the implementations and the you know, product itself depends. It can be 5 years, 10 years. Depends where you start, because sometimes you have a good idea when, in fact, you have the laser. A very good example for that is when we invented the eye surgery. In fact, we didn't invent surgery because it was an accident. We discovered it completely by a true accident. Okay? And so this is when one of my students was working on the laser. His name was Ditardu. Very nice students. And you know, it was in early days of the laser, especially this pulse laser, very powerful laser. Normally, you know, wearing glasses is absolutely mandatory, you know, in the lab. But if you are working sometime, you know, in the early days, with this type of glasses, you couldn't see what you were doing. So the students, you know, were having glasses to protect their eyes, but when they were doing to a critical adjustment, they were doing this, you know, and they, you know, they were doing it. And it happened, and my student got the laser in his eye. So he came, and he says, he came in my office, he said, Gérard, I got the laser in my eyes, and I'm sorry, because he was really sorry because he thought that they were going to close my lab, close the lab. So he was already apologetic, you know, and because he's Asian, some are often like this. And I said, don't worry, we go to the hospital. Okay, we go to the hospital, and then another student, medical student this time, was amazing, came and looked at the eye of Ditar, and he was amazed. He said, what kind of laser is that? Because they are using lasers but not this type of lasers. And he said, you know, it's amazing. And so Ditar, the student said, what is amazing? He said, because you got hit by the laser, you have a damage, but the damage is perfect. And it's a true story. By the way, at Stockholm, when I got the prize, you know, you have to talk about what you have done, and I told them, and so someone asked a question at one point. He said, "What happened to the students?" And he says, "Okay, he's here." in front. He was in first row, and he was okay because it was a very sharp damage and very small, so the brain could compensate after a while. So he's fine. But of course, this is a major. So this, to give you an idea, this is really what we call serendipity. Sometimes you find something by serendipity. Christopher Columbus found America by serendipity. He was not looking for it. He was looking for China. He was looking for. So this is what I'm saying. It's when you do research, sometimes you are lucky. Okay, but it's not always. I don't want to say, have an accident in your research and you would be, happy. Yeah. So of course, we went very fast after that because we had the laser. So we had to do all these animal studies and so on. So it took years, especially, when you are talking about medical. When you are, they are very, very careful, and you have to go through all these steps, precisely. But otherwise, we had all the basic elements right there. Yeah. Of course, this is very important questions, because if you want really to, to develop a product and things like this, yeah. Yes.
Thank you very much. Professor, very much for coming. We heard about you about 4 years ago in connection with Professor Aluti, that you were supposed to have come because you were his friend. And I'm very glad that this evening we have seen you in flesh and blood. And I must say that I've really enjoyed what you presented this evening. But I'm very much intrigued by the fact that you said you won the laureate Nobel Prize with your student. But you said earlier on that it took 25 years from the concept to going to Stockholm. Is your student as old as you, or he was given the prize because he worked with you? I wanted to know what led to the student sharing the prize with you.
You mean if it got done?
Why the student shared the prize?
Yes, yes. How did it come about? Because
Well, I mean,
Donna Strickland.
yes. Donna deserved it. And the committee, Nobel Prize committee, are very, very careful about that. And the way they go is we wrote a scientific paper. Of course, when we did it for the first time, this work, we had the scientific papers, and she was the first name on the publications list, and they thought that, so we are only two. Sometimes it's a problem when you do research because you have many, like the Higgs boson, for instance, where you have 5,000 people. It takes a book of authors. No, here and also, I mean, they are very careful because they are inquiring, with others and so on. But no, I think they did a good job, and they did the right job. In fact, the right thing to do was to nominate her as a Nobel Prize. Yeah. But you know, 35 years is a very typical. For instance, Ashking, who was already when I started my graduate research, we were talking about Ashking as a Nobel winner. And we had, so many years, 40 years after, when Ashking got the prize, it was in fact 2 years ago. I mean, he was 96, but he didn't live long after that, unfortunately. But he was, he knew that he was going to get it, but he was a little bit pissed off not to get it, you know. He got it, but he died a few years after. Yeah.
Sir, good evening. My name is Edward Aglija, a student of Accra Technical Training Center. My question is, what are the advantages of leisure? Like, we have disadvantages and advantages in everything. So I want to know the advantages and the disadvantages, both of them.
Like, what are the advantages? Was the question, what are the...
Yeah.
So, if I understand your question, you're asking what are the advantages and disadvantages of the laser? Well, maybe I can say some things you shouldn't do with a laser, like, shine it at an airplane so that it might hit the pilot's eyes or something. So people play around with that, and they get arrested. Use a laser because it's a very powerful light. So you don't want to shine it in people's eyes. So. But other than that,
or maybe you can discover, ophthalmology. This is what I think.
Yeah. Yes.
So you never know.
Yeah. Like every powerful instrument, you have to be careful when you're using it. And happily, the accident that happened to the student, it didn't cause any permanent damage. And in fact, just a couple of months ago, the student, along with Professor Mourou and a couple of other co-workers, were awarded the Golden Goose Prize for serendipitous discoveries that have benefited mankind. Right. So the student ultimately got a reward for all his pain. Yeah.
Mm-hmm. Yeah.
Sorry. Prof, good evening once again. So this question here is basically for us students. It's in a tie-in with what Prof. Kaufman asked. 25 years it took you to come to this point in terms of this particular achievement. So as students, we know it's going to be a hurdle. There were hurdles and then predicaments and challenges you had to cross. Could you enumerate or tell us some of them, if possible, that you faced in your way to achieving this dream and how you're able to overcome them? Thank you.
How to get to Nobel Prize?
Some of the challenges you encountered to get into this point,
yeah,
and how you overcame.
Yes. Well, I mean, my I never had the Nobel Prize as my final objective was not to get the Nobel Prize. But I was passionate by physics, you know, and you see, there are so few Nobel Prizes, but you think, trying to dedicate yourself at the beginning to get it, I think is maybe not a good idea, okay? Because there is a Nobel Prize, it's only one thing, but there's so many other things really to enjoy in life. If you just think about that from the beginning, you may miss other opportunities. So it has never been my drive for me. I mean, it was not a drive. Nobel Prize was not a main drive to get for me to move in science. But it's always like this, you know. I mean, you have to love what you are doing. Okay, you have to be passionate about what you are doing, and then you know, things happen. Yeah, I see a student here. Yeah?
Please, I'm Tosi Beniza from Ganata Senior High School. Please, I would like to ask a question about the application of lasers in the space debris. In some cases, the space debris is as small as a centimeter in diameter, and they are moving at about 10 times the speed of the fastest bullet. All right. So how would a stationary satellite, or one moving at a relatively slower speed as the space debris, manage to focus a laser beam on it in order to push it into the Earth's atmosphere? Something of that sort.
Could you maybe move here so I can hear the question and get the applause?
Please, I wanted to ask if okay, so in the case of the space debris, the space debris are as small as they are as small as a centimeter in diameter. And
Very, very small.
And they're moving. Okay, so it's like the fastest bullet. Like, okay, the bullet from the fastest gun produced is. So if a space debris moving is supposed to be pushed into the Earth's atmosphere by a stationary satellite or one moving at a relatively slower speed as that of the debris, how would that manage to be done by?
Well, I mean, the atmosphere is going to burn the debris. This is what happens when you see a shooting star. Shooting star, you know, is a meteorite, you know, something coming from the outside the Earth, getting into the atmosphere and becoming extremely hot. And a lot of shooting stars don't even reach the ground because they are burned in the atmosphere. So the idea with the laser is trying to convince the debris, you know, to change orbits because they are orbiting. So they can orbit for 100 years, 1,000 years, you know. But of course, there are a danger. You know, if you're astronauts now, you send astronauts in space, they may get it. They may get the debris. So you like try to clean it. And to clean it, you know that what you want to do, you have to convince the debris to go into the atmosphere. And so what you do, you aim the laser at the debris. When you detect it, you have telescopes and things like that to help you. And then when you see it, you get it, you send the laser, and the laser is going really to what you want is not to blow to be careful about you want to blow the debris, because you are going to fracture the debris, and you are going to have many debris. You know, and that's not what you want. What you want to get rid of it. So you ablate the debris by focusing the beam just on the debris. So you just are going to ablate a small chunk of the debris. But when you do ablations, you know, you have what we call a rocket effect. We have a rocket effect because, you know, you have the stuff that the ablations leads to that, because you have these fusion reactions, you know, rocket effect. And bang, that's going to deorbit the debris. And when it's in the atmosphere, it will be burned.
In a case where the space debris is moving at quite a high speed, would the satellite manage to also move at that speed to be able to focus that laser on the debris?
Sorry, could you repeat the question, because I may not understood it.
The satellites move at quite a slow speed compared to the debris in space. So is there a way to, in a way, increase the speed of the satellite so that they'll be able to, in a way, like chase the debris so as to focus the laser on the debris so that the whole process can be made? Or
can you help me?
I've been given a sign that need to get finished now.
Yeah.
So maybe we can take up your question later on, because I've gotten a sign that we need to close the question and answer period at this time. But maybe afterwards.
Well, we can. Yeah. Let me step down. Yeah. Good.
Thank you very much for the questions.
Well, thank you. Don't go anywhere. Don't go anywhere.
Watch out. Let's thank great talk and thank all the
Thank you, everybody.
Now, the chairman will now have some closing remarks.
Ladies and gentlemen, we have been treated to a very exciting evening. Let us show our appreciation again to our speaker. He has brought us to a point of better appreciation of the applications of laser in medicine, in power generation, environmental control in the atmosphere. And I would like to repeat his adage, the best is yet to come. Thank you, Professor Mourou. On behalf of the Academy, fellows, and our invited guests, we wish you all the best as you proceed to Senegal.
Yeah.
And your further interaction with other audiences on this inspiring journey you have been on. Thank you. And we want to thank the Embassy of France for your support, and your wife.
Oh, absolutely.
Yeah, to come. I'm trying to get her attention. We are thanking you.
We are talking about you.
We want to thank you. So have a pleasant stay in Ghana before you move on to other countries. Yeah. Thank you very much. I will invite the Honorary Secretary to give us a few closing announcements for this evening. Thank you, Prof.
Thank you very much. All the best. Thank you for having me.
Thank you very much. So let me thank Emeritus Professor Sefadede, the President of the Academy and Chairman, for this evening for his closing remarks. A round for him, please. Thank you. We have come to the end of this exciting evening. All good things, they say, must come to an end. Let me acknowledge our wonderful audience, the students who have been here with us, and they are from Accra Technical Training Center. And the other school here is Ganata Senior High School. Thank you very much. You've been very active and engaging. As we leave here, there's a refreshment that has been packaged for us. And so pick up your share as you leave the auditorium. Now, our students, there is good news for you. Professor Mourou would like to have a group picture with you. So, when you leave, please wait just outside. Don't go away. Well, unless you don't want to be in the picture. I know I would like to be in it. Yeah. And thank you, Professor Mourou, for this idea. So he wants to take the pictures here with you in groups, and so maybe Fred, if you can help them to arrange themselves. Yeah, let's be quick about it.